Hello, I will talk about special relativity. Uh, I will talk about three phenomena that occur when someone is traveling at very high speed, close to the speed of light. The first phenomenon is the increase in mass. The second phenomenon is length contraction. And the third phenomenon is time dilation. I will start with the increase in mass. Suppose, first of all, the equation is for the increase in the mass is m equals to m naught divided by the root of 1 minus v squared divided by c squared. So m actually is the mass of a body or the human being that is moving in a very high speed in the space or spaceship. And m naught is the rest mass, that is to say the mass on Earth when the body or the object is not moving at all. So the mass or the increase in the mass of the object or the human or the body is m, that equals to the mass of the body on Earth, that it is not moving, divided by the root of 1 minus v squared divided by c squared. So suppose the twin brother who goes on a journey in space weighs 100 kilogram on Earth. So we will use that equation in order to calculate what will be the mass of a man that is traveling in the spaceship at a speed of 80% of the speed of light, that is 240,000 kilometers per second, and his mass on Earth is 100 kilogram. So what will be his mass when he travels in the spaceship at 240,000 kilometers per second? So the mass will be his mass on Earth divided by root of 1 minus 200,000 kilometers per second squared divided by the speed of the light squared. And the final result is 167 kilograms. So if the twin brother on Earth his mass weighs 100 kilogram, when he goes to the space and travels in the speed of 80% of the speed of light, that is 240,000 kilometers per second, his body mass will increase. It will be 167 kilograms. As I have already said, the m naught is the rest mass, that is to say the mass of the body or the object when it is on Earth and it is not moving. Okay, So according to the mass increase equation of spatial relativity, his mass in space will be about 167 kilograms, as we already calculated. Yes? But he will not feel it at all. If his twin brother has a mass detector, the detector will measure 167 kilograms. That means that his mass has increased by 67 kilograms from 100 kilograms to 167 kilograms. Okay. Now I will continue to talk about the second phenomenon that occurs when someone or an object moves in the space of a spaceship at very high speed. The second phenomenon is the length contraction. As mentioned, the distance from Earth to the star Epsilon is 10 light years, and actually the equation is L, that is the final length or distance after the distance shrunk or shrunk because of the fact that the body or the object is moving at very high speed. So the distance between Earth and the star Epsilon will be shrunk to 6 light years, only from 8 light years to 6 light years. So L is the distance from the object that is moving at very high speed to the other object, for example, the star Epsilon, and L naught actually is the distance that you measure from Earth to the object. For example, the distance between Earth and the star Epsilon, when you measure it from Earth, is 10 light years. And L is the distance after it shrinked because of the fact that the body of the spaceship is moving at very high speed. So L equals to L naught times root of 1 minus v squared divided by c squared. And in our example that I gave in the previous lecture, actually the distance L naught from Earth to the star Epsilon as measured from Earth is 10 light years, and we multiply it by the root of 1 minus the speed of the spaceship divided the speed of the spaceship squared divided by speed of the light squared. So the distance between Earth and the star Epsilon has shrunk to 6 light years only, from 10 light years to 6 light years, because of the fact that the spaceship is moving at very high speed, at the speed of 240,000 kilometers per second. Okay? As mentioned, the distance from Earth to the star Epsilon has shrunk from 10 light years to 6 light years only from the point of view of the brother flying in the spaceship. But in addition to that, the height of the man in the spaceship also shrinks. And if on Earth height is 1.8 meters, then from the point of view of the twin brother who remains on Earth, the height of the twin brother in the spacecraft shrinks to only 1.08 meters. So the L is the height of the brother after it shrink, because it is moving at very high speed in the space. Actually, in our example is 1.08 meters, and N naught is the height of the twin on Earth, that is 1.8 meters, and we multiply L naught by the root of 1 minus v squared divided by c squared, and the result is 1.08 meters. So his height is shrunk from 1.8 meters to 1.08 meters only, and his height is actually shrinked at 72 centimeters, because on Earth is 180 centimeters, and on in the spaceship, when he travels at 240,000 kilometers per second, his height will be only 1.08 centimeters, or 108 centimeters only. So if the brother that stays on Earth had a height detector, then the detector would show a height of only 1.08 meters. But the twin brother who is in the spacecraft doesn't feel that he is shorter. Okay? So, as I have already said, L is the height of the twin brother that travels at the speed of 240,000 kilometers per second, and L naught is the height of the brother that travels in the spacecraft, is the height, L naught is the height of the twin brother that travels in the spacecraft, his height on Earth. So when the twin brother that travels in the spacecraft at very high speed, when we measure his height on Earth, his height is L naught, that is 180 centimeters, as his height when he is traveling at the velocity of 240,000 kilometers per second, his height will be shrunk to 1.08 meters, or 108 centimeters only. Okay, so Now I will talk about the time dilation. As I've already said, as I have already said, when something or someone is traveling at very high speed in the spaceship or in the space, there will be the phenomenon of time dilation in the spaceship. As mentioned, from the point of view of the brother who is on Earth, his twin brother is moving in the spaceship at very high speed. Therefore, the rate of time flow in the spaceship will be slower than the rate of time flow on Earth. And while on Earth it took 25 years for the twin brother to return from a journey in space, in the spaceship the time that will be passed is only 15 years. Because of time dilation, as I have already explained the equation, t is the time actually the time dilation itself, or the time that is passed in the spaceship, and t naught is the time that is passed on Earth during all the journey, and we multiply it by the root of 1 minus 3 squared divided by c squared, and we get, as I already said, the t, that is the time that is passed on the spaceship. Okay? So in our example, on Earth, the time that is passed during all the journey is 25 years, and we might multiply it by v squared, that is 240,000 kilometers per second divided by the speed of light squared, and v divided by c is 0.8, and we square it, and actually 1 minus 0.8 squared is 0.36, and the root of 0.36 is 0.6, and 0.6 times 25 equals to 15 years. So in the spaceship, the time that is passed is only 15 years, 10 years less than the time that is passed on Earth. So the twin that is in the spaceship and travels at very high speed will be 10 years younger than his twin brother that stayed on Earth. Okay. While from the point of view of the twin brother who embarked on a spaceship journey towards Epsilon star, yes, he is not, he is at rest. The brother in the spaceship, he is, according to the point of view of him, he is at rest, and the Epsilon star is moving towards him at a speed of 240,000 kilometers per second. Therefore, in this situation there will be a contraction of distance according to special relativity. And the total distance between the Earth and the star Epsilon will be 6 light years only, and the round trip distance is 12 light years, and at the speed of 80% of the speed of light, the entire journey in a spacecraft will take 15 years due to the contraction of distance between the spaceship and the star Epsilon as mentioned. So you can see there that the total time that is passed in the spaceship t equals to the total way that the brother in the spaceship does, that is 12 light years, and it does it in the velocity of the 80% of the speed of light, because the units is in the light years, so also the speed also is 0.8 light 0.8 from the speed of light, so it's the same units. Here is 12 light years, and also here is 0.8 of the velocity of light, so it is the same units. So when we divide the total way that the brother in the spaceship does in the speed, we get the total time, that is 15 years, that is passed in the spaceship. Only 15 years. And actually the two brothers agree that the brother in the spaceship will be 10 years younger than his brother that stays on Earth. And I will repeat again that according to the brother in the spaceship, he is at rest, and the star Epsilon moving towards him at the speed of 240,000 kilometers per second, and in this situation there will be a phenomenon that is called a contraction of distance. So the distance from Earth or the spaceship to the star Epsilon will be shrinked to 6 light years. From 10 light years it will be shrink to 6 light years. And because it does the journey back and forth from Earth to the star Epsilon, so it is 6 light years in one direction and plus 6 light years in another direction. The total way that it does is 12 light years, and does it in the 80% of the speed of light. So the total time that it will take him to do all the journey will be 15 years, as already as the same time that is passed in the spaceship from the point of view of the brother that is on Earth, and there we already said that because of time dilation, the journey will take only 15 years, and there from the point of view of the brother in the spaceship, because of contraction of time, the journey will be only 15 years. Okay? Thank you very much.